Well, is this am I on mic? Oh, fantastic. So thank you all so much for coming out. This is kind of exciting for me. This is going to be the first time I've ever actually given a talk at a PyCon. So here goes nothing. Now, overall, Python is a pretty great language. It's got a pretty fantastic community, tons of packages, straightforward syntax. And for the most part, it isn't very surprising. But only for the most part. Every now and then, you're going to run into some weird kind of problem. Something that you can't explain, your coworkers can't explain, even that really smart friend you met at a meetup, even they can't explain it. And this is when the rubber really hits the road. This is when you need to draw on all those years of experience you have as a programmer, all those thousands of dollars you've put into your schooling, and prove to yourself and to the world that you are, in fact, a true programmer. But I'm here to tell you that there is another way. It might not necessarily be a better way, or even, for that case, a very good way, but it is definitely more interesting. So in this talk, I'm going to be taking a Stack Overflow question that I found really fascinating about a year and a half, 2 years ago, that's looking at some strange performance characteristics. I'm going to be digging into that code using dis.disassemble to take apart the Python, turn that into bytecode. Then we're going to dive into the Python virtual machine and the C source code for Python itself to see what's actually going on under the hood. Hopefully by doing that, and by doing that, I'm going to be showing you how when you find yourself in a similar kind of situation, you can, from first principles, go through and solve it for yourself. Now, if this is all kind of old hat to you, if you've done that before, I won't be offended if you want to get up and leave. Brett Cannon's down the hall doing a Python 3.6. That's kind of cool. Oh, neat. And so on the Python version thing, all of my examples are going to be Python 2.7, but everything I talk about would transition completely to 3. Now, I mean, with PyPy and other things, I'm not exactly sure how well that's going to work, but I'm a CPython person. So here's that question. Why is x in tuple x faster than x equals x? At first, that's pretty strange. I mean, equality is about the most straightforward thing you can do, where tuple membership is obviously a little bit more complicated. But even after profiling it myself a bunch of times, I was able to consistently, across Python versions, across machines, reproduce the same result. So just as an aside, if you haven't used it before, IPython's %timeit is super, super fun. Instead of using the timeit module, which you have to fiddle with the numbers and it's kind of difficult, timeit automatically figures out how fast the snippet is and scales the number of loops that it runs accordingly. But anyway, back to our problem. So when I saw this question, it was intriguing. I was able to reproduce the results, and I wanted to dig in to see what was going on. But where do we start? The first step is going to be dis.disassemble. Dis.disassemble lets you disassemble Python code and see the underlying bytecode. Now, you've probably heard about Python being talked about as an interpreted language as compared to compiled languages like Java or C++. But this actually isn't strictly true. Python does have a compiler, and it runs over all the .py files when you import them or export them. And it's actually the PYC files that are littering your system. That is the compiled bytecode. So dis.disassemble lets us see that bytecode and translates it into a kind of human-friendly form. And here's a quick example. There's a lot going on here, so we're going to break it down one chunk at a time. First, we've got our kind of standard function definition. This should be kind of old hat to everyone. Nothing at all surprising is going on there. Second, we've got that call to dis.disassemble. But this is where things start to get a little bit interesting and you might not be familiar with. So what's that func under code attribute? To understand, we need to dig into function objects. So functions, just like everything else in Python, are objects with a bunch of attributes, and we could use the dir built-in to list all those attributes and see what's going on there. there's a whole bunch of super cool stuff, and I would really, really encourage you after this talk to play around, poke around at some of those. The func globals, func defaults is kind of neat. But for now, we're going to be focusing on func code. So just taking a quick look, we can see that it's an object that describes the code associated with a function. It tells us what the function's name is, where it's defined, what line of the file. And there's a whole bunch of other stuff, which again, it's super cool if you want to dig in for yourself and just experiment, see what those do, Google them around a little bit. But unfortunately, we don't have unlimited time, so we need to limit ourselves just to the CO under code attribute, because this is the one that the dis module is looking for. CO under code contains the bytecode for that function. This is actually the raw bytecode. If you were to save this function to a .py file, run Python on it, and then look inside the .pyc file, you would find exactly these bytes. We can also use disassemble string, excuse me, to disassemble those bytes. And you'll notice, if you remember, because I'm sure you are all paying a lot of attention to the last slide, those are actually the same opcodes, the same instructions. We're missing some things like line numbers and names, but the functionality is still there. Now, one piece of homework, if you're interested in this, is you'll notice that in that bytecode, we don't have that string, that hello %s format string. So see if you can figure out where that's actually being stored. But anyway, oh, right. So we're actually doing OK for time. So I want to dig into the func under closure just a little bit, because it's really, really cool. So for those of you who aren't familiar with a closure, basically what a closure does is it lets you have a function that keeps track of references to variables that weren't defined inside it. So for instance, in this hello closure function, we can see that it references this message variable, but that message variable is actually being defined outside of the function. But when the function is returned, it still has access so it can use it later on. Now, how does that work in Python? I'm glad you asked. It uses the func under closure attribute. The func under closure attribute contains a tuple of all the variables being stored over. Okay, so actually it has these things called cells, and a cell has a reference to the variable, so that if the variable changes in the outer function, the inner scopes can keep up with it. But we don't need to get into details. And one really cool consequence of this is that it's actually possible to take a closure, serialize it entirely, send it over the network, deserialize it on another machine, and have that other machine run it just as easily as the computer it was built on. I've never seen that done, and it strikes me as possibly being a bit of a bad idea, but I would absolutely love it if one of you wanted to go and actually build a thing for doing that and show it off. I would tweet the heck out of that. Anyway, so a little bit of homework here too, just if you're interested, is notice though that there are actually two variables that are in scope of the inner closure. But the func under closure attribute, the tuple that contains those references, is only one item long. So see if you can dig in and make a guess as to what's happening to that other variable. Anyway, that was a bit of a digression. Let's get back to the problem at hand here, disassemble. So we know what that line is doing now, and we know what's going on a little bit more. We know what this disassembled code is. So let's just purely guessing here based on context what's going on. So the bytecode here is loading a constant, the string hello, loading a global, the variable what, building a tuple, so that's the function that actually takes the variable, sticks it in a tuple, running the binary modulo operator. So this is actually one of the things I found really cool about Python. I'm sure you've all used the % formatting strings like foo, %bar. But what you might not realize is that % is actually exactly the same % that you use when you're saying number modulo bigger number to make sure that you're cycling through an array instead of going off the end. And finally, we're storing that value, the formatted string, back into the message variable. Next line is pretty straightforward as well. Loading the message, printing it, and returning none at the end of the function. We don't have a return statement. Python sticks one of those in for us. So I want to go into just a little bit more detail on actually what's going on here, because those of you who have fooled around with assembly and that sort of thing, this will be old hat, but this was pretty cool to me when I learned about it, so I hope you'll find the same thing. You've probably noticed that, that these instructions here are really simple. They just have the one instruction and one argument, and some of them have no arguments. That's because the Python bytecode interpreter, it's also called the Python virtual machine, I'll probably use those two interchangeably, it's designed as what's called a stack machine. So a stack machine, in a stack machine, the instructions use a stack to pass values back and forth. So if I'll show you an example in a second. And now this is in contrast with a register machine, like an x86 processor in your computer, an ARM processor on your phone. Those are register-based. I had a whole bunch of slides explaining that. It's really boring. I took them out. So to give you a concrete example, let's say we're evaluating 1 + 2 × 3. If we were to convert it to some like imaginary stack machine instructions, we would have a load 1. So the load 1 will execute, and it will put a 1 on the stack. A load 2 sticks a 2 at the end of the stack. Load 3, so now we have 1, 2, 3 on the stack. Then we call a multiply. The multiply is going to grab the top 2 values from the stack, multiply them together, and stick the result back on there. So we get 6. And finally add. Add again, we'll pop the top 2 values off the stack, the 1 and the 7, or 1 and the 6, add them, number 1 back on the stack. Stack machines are used especially in interpretive programming languages. Some implementations of Ruby use them. Python definitely uses them, obviously. Java, Ethereum, the cryptocurrency, uses one. And the reason is that they're really fast and simple to implement in software. And they're also amenable to a lot of optimizations like the just-in-time compiler stuff. But that's another, again, a whole nother talk. So that was a lot. Time to get back to the problem we have at hand here. Why is tuple membership just like a tiny bit faster? So the first thing that we're going to be doing is using dis.disassemble to pull apart those comparisons and see what's actually going on under the hood. In the case of in, we load 2 constants, the first one being the string x, the second one being a string, a tuple x with a tuple with a string inside it. We run compare with the argument in, so that's the in comparison, and we return whatever that returned. Equality is almost identical. And by the way, these numbers here, if you were curious, they reference the slot in the list of constants, the function constants, that value appears in. And we'll get to that. I'll get to why that's interesting a little bit later. But anyway, we can see that they're basically identical, except the one uses the tuple and string, and that instruction 6, the compare op, the argument is different. So what's going on here? Well, obviously at this point, this is where we start leaving Python code land and we have to start digging into C code land, because these are implemented inside the Python virtual machine itself, the Python executable. And to do that, I mean, fortunately, the Python source code is fantastic. It's very, very readable. Even if you know nothing at all about C, I would almost guarantee that you could pick it up and start reading through it and seeing what's going on with only, a little bit of Googling. So what I'm going to be doing here, we're going to download tarball, extract it, and search through for that just that string compare op. And hopefully you're kind of seeing that there's nothing magic here. I'm not really relying on any knowledge that I wasn't able to get just from the things I see on my screen. Anyway, so there are a few things that come up, but I'm going to take some shortcuts and just tell you the two that are kind of most interesting. There's that Python ceval.c and Python peephole.c. Now, peephole.c is super, super cool. It does these in-place micro-optimizations on the bytecode. So, for instance, if you have a not A in B in your source code, the peephole optimizer is actually going to transform that into an A not in B, because A not in B is just one instruction versus the 2 instructions that not A in B needs. I'm not going to go into any more details, but Alison Kaptur, has a really, really neat blog post where she digs into not just what it's doing, but some of the neat consequences, especially the consequences when it comes to code coverage tools. By the way, I'm going to have links to all these things at the end. So, that. ceval.c, though, is where we want to look. Just a quick reminder, this is the bytecode that we're dealing with. And now we're going to jump into ceval.c. Please give me. And if you're interested, by the way, my slides are all up on my Twitter account @Wolever while I switch these things over. So you can play along if you'd like. How's that going? Can everyone see? Too small, too big? Good, good, good. So here is where we're going to start our journey. I've opened up ceval.c in the Python source. And you can see this target macro, target compare op. For those of you who know C, the outer statement here is a big switch statement that is switching on the operation being performed, switching on the bytecode instruction. And the target lets us, the target was actually added around 2.2, 2.3, sometime with these computed goto optimizations that actually lets this kind of really tight core loop of Python run a bit faster. I've got links in the documentation, in my slides, to a deeper dive into that. And again, it's really cool what's going on there, but we don't have time to do that now. Instead, we're going to start reading through this function and see what happens. So first thing we're going to notice here is the v and w pop and top. What that's going to do, that's going to pop an item off the stack, and that's going to peek at the top item on the stack, leaving it there. Then we're going to do this pyint check exact. Now, I mean, I'm guessing from context, I haven't actually read the code on that one, that what it's doing is checking to see if w, the first argument, and v, the second argument, are exactly integers. And actually, this is kind of cool. This is one of the things that I learned while I was doing this talk is when you're comparing integers in Python, there's this very, very optimized thing, so it can be significantly faster than comparing literally any other type. We're not integers, though. We're dealing with strings. So we're going to be coming down and following this, this branch in the code, comp outcome. And the three arguments that we're passing in here, opt arg is going to be either equals or in. V and w are the two arguments. So one of the things, just as an aside, as you're reading through code, it's super, super helpful to learn how to do jump to definitions. In Vim, I'm using a tags file. You might have noticed the call to C tags in the first slide. Sublime has a go to symbol in project. I'm sure every single IDE has this. And you'll see how quickly I'm able to move through. And when you're reading code, you're going to want to figure out how you can move through just as quickly, because it's going to save you tons and tons of time in comparison to like grabbing through for every definition you want to go to. Now, so first we're going to look for that double equals and follow what happens in the double equals branch. Switching on the operation, it's not is, it's not. Go down here, not exact match. So we fall through, and we must be going back to this PyObject rich compare function. And again, it's being passed the two arguments in the operation. Again, reading through here, there's some stuff about recursion, making sure we don't blow up the stack. And this is the first branch point. Now, if you're not totally familiar with C, this might look a little bit weird, these little arrows. You can think very, very roughly of the left-hand sides, kind of like objects. There's a bunch of important differences. They aren't, but for these purposes, it's close enough. You'll also notice that the attributes all have a common prefix. I'm not actually sure exactly why, maybe for readability, maybe for ease of navigation, but it's a really common pattern in C to prefix, to have all of the members of a type share the same prefix. So the OB under prefix is for PyObject, the C type that is shared by every single object in Python. The second thing that you're going to notice here, so first, let's say the V, this check here to see if the V type is equal to the W type. What that's doing is saying are these identical? Are these both strings? And in this case, yep, they're both strings, so we know that's going to pass. The second thing here that's kind of neat is this PyIsInstance check. Now, if you've ever accidentally added an old style class to your program, maybe, and you would have done that by leaving out the object portion of class foo object. And you might have noticed that it behaves in some kind of funny ways. It's going to be a lot slower, like property decorators aren't going to work, a bunch of things aren't going to work. And that's because you accidentally created an old style class. You can look up the history there if you don't know much about it. It's kind of a neat transition that Python went through. But the critical thing is old style classes in the C source code are called instances. And since they behave so dramatically differently, all over the place, there are these little checks to see if we're dealing with like an old style class or the new cool thing. So moving on down, the next thing that we notice is grabbing this rich compare method, this rich compare function out of the left-hand side of the comparison. Under the hood, this is the line being run, so we want to look for this TP under rich compare object. Now I mentioned that prefix. TP is the prefix for Python types. Py object type, excuse me. So we're going to grab that rich compare out, and we can kind of reason that, yeah, like probably there's going to be a rich compare, so it's not going to be null. And we need to now look and find it, because if it's easy to miss, but this is the line where that rich compare function is actually called. It's a little bit more obtuse than Python would be for a similar operation. And to look up and find where in the source code that's, which function in the source code is being called, we need to guess what that type is. Now, if you were to poke around, any of you in 5 or 10 minutes would easily see that the type is going to be PyString. So we're just going to jump to that and take a look at what's going on here. Now, I find this really, really cool. This is how all of the core fundamental types in Python are defined, so like your strings, your lists, your tuples, integers. There are these big structures with just a bunch of different attributes, and they're all kind of helping with the comments to tell us what's going on here. But if we remember, the one that we're interested in is the rich compare. So we're going to look for rich compare. Oh, look at that. String underscore rich compare. That makes a lot of sense. Again, so we're going to follow through, and this is the function that's getting called to compare those two strings. First thing that happens, obviously, we're checking to see that they are, in fact, strings. And now this is where something special and kind of interesting happens. So thinking back, if you remember when we had that disassembled code, the argument to both of the load constants was the same. And what that means is that both of the strings being compared are actually exactly the same thing in memory. And that's happening because Python does this thing called string interning. If you have strings in a module, if you say, for instance, foo equals ABC, bar equals ABC, when Python parses that module, it's actually going to notice that those two strings are identical and give make both foo and bar reference exactly the same string in memory. Now again, this isn't actually like 100% true. The semantics of exactly what goes on but behind that string interning process is kind of cool. And I've got a link to a blog post there that goes into more detail. But for now, all we need to know is that they're exactly the same thing in memory. So when we come to this, check, if A equals B, we know that that's going to be true because they are identical. We follow that through a couple more lines. We see that the result is pi under true. That's the singleton in the C code that gives us the true that we use in Python. And it gets returned. So now that we know what's happening with the equality comparison, let's pop back up the stack. And in Vim, I'm hitting Control-T to go up, up, up. You can do the same in your favorite editor. And we're going to go back to this comp outcome. Remember, this is where now the first case it was in the first case, the argument was the equals. And now we're going to follow for the in comparison. It's going to be a little bit faster now because we can see comp in is explicitly one of the operators that's being checked for. And there's this direct call to PySequence contains. Tracing through this function, the first thing that we see is this check to see if we have this, if the type, so in this case, the type is a tuple, if it has this sequence in, if it can perform sequence in operations. I'm going to save a little bit of tracing here, and we're just going to jump. We're going to notice that we check for contains on the type, and the type we're dealing with is PyTuple. again, it looks very similar to the string comparison. We're going to look at its sequence methods. And there's this function tuple contains. Now, one of the things I find a lot of fun when I'm reading through the Python source code is if you look at this loop, this is exactly a loop you would write like in your CS 101 course. Yet every time you test membership in a tuple, this is what's happening. It's actually very simple and straightforward. And if we look through, we see the way that the items are being compared is this PyObject-rich compare bool. Now that bool is actually the secret little magic that's making this that makes this faster. Because for reasons, again, that are a little bit beyond me, and in all my digging, I haven't quite found exactly why. The very first this rich compare bool does is it checks the identity. And if you think back and remember that both the strings are going to be identical because of string interning, you'll see that in the tuple membership, we actually much more quickly get to that comparison, and we can much more quickly pop up the stack and give a return value. In fact, tracing through, I went through and kind of traced all the lines of code that are executed. On the top here, we have the equality comparison. And on the bottom, we have the tuple comparison. And you can see that it's just like a few lines shorter. Now, I don't want disk utility displays. I'm going to stick you back into my slides. Now, I realize that was just a little bit anticlimactic, and probably not as exciting as you'd hope for, but you know what? You're all programmers. You know that programming really isn't that exciting. But hopefully you've learned, first, that Python isn't magic. There's nothing going on here that we weren't able to take apart and in not very much time figure out. The second thing is it's also not too hard to peek behind the curtains. You can dig through and, without very much experience, without knowing anything about C, you could have figured that exact same thing out for yourself. And finally, I hope you can start seeing the ways that you can take that approach of digging in and figuring out how to dig deeper and deeper and deeper, and deal with the problems you might deal with every day. I mean, it's not often that you'll have that kind of weird performance quirk, but more often than not, you're going to have a problem where a Django model isn't saving, or beautiful soup isn't matching a tag, or urllib3 isn't pooling in the way that you want. And you will be able to take this same approach and apply it there. I've got at the end of these slides a couple notes about using PDB, the PDB debugger. You should absolutely do that. But I'm almost out of time, so I won't talk about that too much yet. The one thing that I will say now is if you remember that first slide, the slide that we opened with, hopefully now you can see what's going on. Even though nan has this weird property that nan isn't actually equal to nan, because the tuple membership and the list membership operator checks identity first, it behaves slightly differently and weirdly. Now, I hope that was kind of interesting. And if you want to dig in and start trying some things for yourself, I've got a little homework assignment here. This will take you probably half an hour if you get my slides and go through it yourself. You know that you can dynamically add methods to an object. But if you have an object with, for instance, a dunder_len method, and you try and override that dynamically, it's just not going to work. So see if you can figure out what's going on there. I've got links in the slides. You can check those. I'm going to leave those up now. And thank you all so much. I hope to see some of you tomorrow too.